Am I audible?
Yes, sir.
Okay.
Yes, sir.
Good evening, Dr. Tikendra Verma.
Good evening, sir.
So it is my privilege to introduce our respected speaker of the today's session, Dr. Tikendra Verma. Dr. Tikendra Verma was born at Bhilai in India, Chhattisgarh, India. He received his Bachelor of Engineering in Mechanical Engineering with securing first division from Pandit Ravi Shankar Shukla University, Raipur, Chhattisgarh in 2006. He did his master degree in thermal engineering in 2009 from Department of Mechanical Engineering, Maulana Azad National Institute of Technology, Bhopal. He has obtained his PhD degree from National Institute of Technology, Raipur. He joined Institute of Technology, Korba as assistant professor in July 2013 to September 2015. Later on, he joined National Institute of Technology, Manipur as assistant professor in September 2015 to May 2020. After that, he has joined Mechanical Engineering Department in Maulana Azad National Institute of Technology, Bhopal as assistant professor in June 2020. Presently, Dr. Verma is working as an associate professor in Maulana Azad National Institute of Technology, Bhopal. He has 3 ongoing projects from different funding agencies like DST, TCube, Seed Grant, and DST Manipur. He has published more than 214 research articles. Almost all are SCI papers in various international and national and international journals. Book chapter, book, and 52 conference papers with high impact factor journals. His present citation is 6,125 with H index 48, I-10 index 109. He has guided successfully 7 PhD candidates, 22 MTech candidates. He has organized many programs as a convener, organizing secretary for different faculty development program, workshop, seminar. He has 6 patents granted and filed 6 patents in India and Australia. He also served as a guest editor for International for Environmental Science and Pollution Research, Springer, Materials Today Proceedings, and lecture notes in Mechanical Engineering. He is also editor of Elsewhere book titled Vegetable Oil, Volume 1, Biofuel Technology, Volume 2, Future of Different Seed Oil. Recently featured in top 2% scientists of the world from India in all fields by a survey conducted by Stanford University. He is an active member of Institute of Engineer, Fluid Mechanics and Fluid Power, Indian Society of Heat and Mass Transfer. He has also organized 4 Karyasala under DST service scheme, each ₹5 lakh. He also serves as potential reviewer of reputed journals like Energy, Energy Conversion and Management, Applied Energy, Fuel, Journal of Cleaner Production, Journal of Building Engineering, Waste Management, Journal of Hazardous Materials, etc., International Journal of Ambient Energy, Journal of Thermal Analysis and Calorimetry, Biomass Conversion, Biorefinery, and many more from other publishers also. Apart from his academic and research background, Dr. Verma has played and won Indo-Nepal International Tennis Ball Cricket Match Series in 2016-17, played 5 times National Tennis Ball Cricket Championship in year 2011, 12, 15, 16 and 17. 3 times awarded Khel Shikhar Swarn Alankaran by Chhattisgarh government in 2011, 2012 and 2015. And I would like to tell all these speakers, those who are working in the area of alternative fuels, biofuels, Dr. Tikendra Verma is a well-known personality in our country, and he is doing very wonderful research work in the area of biofuel and alternative fuels for IC engines. So I welcome you, sir, and I am thankful for accepting our invitation. Dr. Verma is going to deliver 2 talks today. He is going to deliver about the CFD, and in second talk, sir is going to deliver about the biofuels. So I welcome you, sir, and over to you.
Thank you, sir. Thank you for this introduction.
Dr. Mulli, have you made
Yes,
a
sir.
co-host for Dr.
Just
Verma?
give me
Yes,
the,
sir. Sir is co-host.
okay. So now PPT is visible.
Yes, yes, visible.
Okay. Thank you, sir, for this introduction. As sir is mentioned, so I have delivered two topics. The first one is computational fluid dynamics and its application. This is my secondary specialization. The first one is, as Sharma sir told, the biodiesel and biofuels and renewable energy area. So today we talk this computational fluid dynamics and its application, how this CFD code works, then the basic steps of CFD, what are the different discretization methods, how we can start our work in the CFD. And then last, I'll discuss one case study which is related to my work, that is room air flow. Some 2-3 slides I have shown for results. And then conclusion is a general conclusion. It's not any specific case study conclusion. So before starting this, the definition, application, and advantage, why we are using CFD and what is that importance. Best of my knowledge, in this universe, jahan par bhi this fluid flow and heat transfer will happen, we can apply the CFD. It depends on our computer ability. So this is the definition. CFD is the science of predicting fluid flow, heat transfer, mass transfer, chemical reaction, and related phenomena by solving the mathematical equations which govern these processes using a numerical process. In the other definition is the CFD is the analysis of system involving fluid flow, heat transfer, and associated phenomena such as chemical reactions by means of computer-based simulation. So the technique is very powerful and spans a wide range of industrial and non-industrial applications areas. So this results analysis is relevant engineering data like redesign, conceptual studies of new designs, detailed product development, troubleshootings, and so on. So there are a lot of applications for this CFD, like others. If you talk in weather prediction, then biomedical engineering, there are blood flows through arteries and veins. In marine engineering, loads on shores of structures, then turbo machineries, turbine, boilers, chemical process engineering, like mixing of separation and polymer molding also, power plants, combustion in IC engine also, it is using for combustion problems, where the piston moves from TDC to BDC. Water happens inside the combustion chamber. We can see through this CFD also. Then electrical and electronics engineering, like cooling of equipments, including microcircuits, external and internal environments of buildings, which I later we can discuss. Very few slides I have shown in that. Then meteorology, as I told, weather prediction. Then why or how this CFD code works. So from the 1960 onwards, the aerospace industry has integrated CFD techniques into the design and R&D and manufacture of aircraft and jet engines. So more recently, the methods have been applied to the design of IC engine, combustion chamber of gas turbines, and
Dr.
furnaces
Verma,
also.
sorry to interrupt. We are not able to see the PPT. Yes, now it is visible.
Okay, sorry.
No issue.
So other than this, furthermore, motor vehicle manufacturer now routinely predict drag forces under bonnet
Sir, please
airflows
also
and
make
the
full screen.
in-car environment with CFD. The CFD is becoming a vital component in the design of industrial products and processes also. So how does this CFD code works? So the codes are structured around the numerical algorithm that can tackle fluid flow problems in order to provide easy access to their solving power. All commercial CFD packages include sophisticated user interface to input problems parameter and to examine the results. Hence, so all codes contain three main elements. The first is preprocessor, the second one is solver, and the third one is our post-processor. For any software, best of my knowledge, there are three things are very important: preprocessor, solver, and post-processor. In preprocessor, generally we are making a design of that particular problem domain. In solver, we are applied the mathematical equations, and then last is post-processor. In that
Good
we
evening,
can
sir. Sir, sorry for the interruption. If possible, please click on the slideshow button, sir. Slideshow button. Full.
Actually,
the full screen. Okay, okay.
Please press F5.
Now it's okay.
Yes,
Okay,
sir,
sir.
yes, sir.
Thank you, sir. Sir,
Yes.
also, if possible, please pin your screen, sir. Your screen is small and your image will be larger. If possible, please pin your slide sharing screen, sir.
तिवारी क्या बोल रहा है? पिन करने के लिए?
Yeah. Yes, sir. Yeah. Thank you, sir. Thank you so much. It's fine, sir. Thank you so much.
Full screen है ना? Now it's okay. Now it's
Fine,
full
sir. Thank you,
screen.
sir. Yes, sir. Thank you.
Okay. So as I told, there are three main elements in this CFD software in NSYS: preprocessor, solver, and a post-processor. So in pre-processing, it consists of the input of a flow problem or to a CFD program by means of an operator-friendly interface, and the subsequent transformation of this input into a form suitable for use by the solver. So the user activities at the pre-processing stage, like the first one, definition of the geometry of the region of the where we have to interest. We can say that generally the computational domain. After that, we are focusing on the grid generation. Grid generation we can define like the subdivision of the domain into a number of smaller, or we can say non-overlapping subdomains, or we can say a mesh or a control volume. Then selection of the physical and chemical phenomena that need to be modeled. After that, we can define of our fluid properties, like specifications of appropriate boundary conditions at cells which coincide with or touch the domain boundary. Most of the time, the researcher, or we can say in the any R&D section, around 60% of the time they can spend, or we can say devote, to the definition of the domain geometry and the grid generation only. After pre-processing, the next is solver. So there are three distinct streams of numerical solution techniques: finite difference, finite element, and spectral method. So we shall be solely concerned with the finite volume method, a special finite difference formulation that is central to the most well-established CFD codes like CFX, NSYS, Fluent, Phoenix, and Star CD. There are some basic steps, like the first one is integration of the governing equation. The basic governing equation for the CFD is conservation of mass, momentum, and energy. In the coming slides, I'll show some equations also. As we know that the conservation of mass is related to continuity equation, and then conservation of momentum is Newton's second law of motion, and then energy equation is related to first law of thermodynamics. So in this, the following steps, like integration of the governing equation of fluid flow over the control volumes of the problem domain, or we can say computational domain, then discretization, conversion of the resulting integer equation into a system of algebraic equations, then solution of the algebraic equation by an iterative method. So CFD codes contain discretization techniques suitable for the treatment of the heat transport phenomenon, convection, that is transport due to fluid flow, and diffusion, that is transport due to variation of phi, that is variable from point to point, as well as for the source term associated with the creation or destruction of that particular variable and the rate of change with respect to time. And then last is our post-processing, that is only related to our how we can display the results, like in vector plot or in 2D and 3D surface or particle tracking, whatever. So
Dr.
as in the
Verma,
pre-processing,
sorry to
a
interrupt.
huge
Now,
amount of
Dr. Verma, we are in the why we use CFD slide is moving or not? We are able to see. Yes, now it is moving.
no, it's still in that slide only. I have not changed.
Okay. Okay. Thank you.
So in the post-processing, the third main element is post-processing. So a huge amount of development work has recently taken place in the post-processing field due to the increased popularity of engineering workstations, many of which have outstanding graphic capabilities. The leading CFD packages are now equipped with versatile data visualization tools. As I told, vector plots, then 2D and 3D surface plot, grid display, domain geometry, then line and shaded contour plots, particle tracking, view manipulations, and then so on. As I told, in this universe where heat and mass transfer is there, fluid flow is there, we can apply the CFD. For any type of problem, we can apply, for engineering, we can apply this computational fluid dynamics. These are the applications of COT, which I have already discussed: flow and heat transfer in industrial process like boiler, heat exchanger, combustion equipment, pumps, blowers, pipings, aerodynamics of ground, vehicle, aircraft, missiles, film coating, thermoforming in material processing applications, flow and heat transfer in propulsion and power generation system, ventilation, heating and cooling flows in buildings, chemical vapor depositions for integrated circuit manufacturing, heat transfer for electronics package applications, and many, many more. So in engineering, for our students, for BTech, MTech, and PhD, there are three basic methods which we have applied for any type of work. That is experimental method. The second one is our analytical method, and the third one is our numerical method. So just like every coin has a different side, head and tail, similarly for this also, experimental, numerical, and analytical, there is some advantages and disadvantages. Like in the experimental method, these are used to obtain reliable informations about physical processes that are not well understood. Example, combustion and turbulence. It may involve full scale, small scale, or blow up scale models. The major disadvantages of this experimental investigation are high cost measurement, difficulties, and probe errors. So small scale models do not always simulate all the features of the full scale setup. So the advantage is that it is most realistic. When we talk about analytical method, so analytical method are of classical mathematics, which are used to obtain the solution of a mathematical model consisting of a set of differential equations which represent a physical process within the limit of assumptions made. Only a handful of analytical solutions are available in heat transfer and fluid mechanics because analytical methods are inadequate in handling complex boundary and non-linearities in the differential equations. Furthermore, this second method, analytical method, solutions often contain infinite series, special functions, or transcendental equations for eigenvalues, and so on. So the numerical evaluation of which becomes quite cumbersome. Then the third one is numerical method. In that, numerical predictions works out the consequences of a mathematical model, but the solution is obtained for variables of discrete grid points in the computational domain, in contrast with analytical method, which gives closed form solution at all points, theoretically infinite number of points in the solution domain or continuum. So the major advantage of numerical solution are its abilities to handle complex geometry and non-linearities in the governing equation or boundary conditions. Other advantages of numerical methods are like low cost, high speed, complex information, ability to simulate realistic conditions, and ability to simulate real condition. Like suppose if you talk about low cost, so in that, while prices of the most items are increasing, so cost of computing is going down every year. When we talk about high speed, so in the last 20 or 30 years, there has been a 1,000-fold increase in the speed of arithmetic operations of computers. Then complete information. A computer simulation gives detailed and complete information of all the variables over the computational domain. Then ability to simulate realistic condition. For a computer program, there is absolutely no problem in having an area of size 10 kilometer cross 10 kilometer or 10 raised to power minus 6 meter multiply 10 raised to power minus 6 meter, or we can say 5,000 degrees Celsius or minus 100 degrees Celsius. So this type of hazardous or flammable material also we can simulate in the CFD. And then last, ability to simulate real condition. In that, there is no problem in idealization like two-dimensionally insulated or isothermal boundary, infinite reaction rate, and so on. So on the other hand, it is extremely difficult, if not impossible, to set up the same in the experimental method. There are some disadvantages also, like in the numerical prediction, these are the associated truncation error and round-off error, and the difficulty in simulating complicated boundary conditions also. So these are basic partial differential equations which we are using in the CFD. According to our problem, we can change this. There are three basic equation which is well known. This linear second order partial differential equation in two independent variable are further classified into three conical form: elliptic, parabolic, and hyperbolic. You can see the general form of this class of equation is, then there are b square minus 4ac is less than 0 elliptic, equal to 0 is parabolic, and greater than 0 is hyperbolic. So for heat transfer, mass transfer, or diffusion equation, we are using this parabolic, the second one, b square minus 4ac, which is useful for our in parabolic problem. The solution advances outward indefinitely from known initial value, always satisfying the known boundary conditions as the solution progresses. This is also called merging type of problem and the open-ended type of solution domain, which we can see in this one, the second diagram, parabolic problem. You can see in this diagram, the one side of the problem, or we can say open-ended type, this diagram. So in elliptic problem, the function of xy must satisfy both the differential equations over a closed domain and the boundary conditions and the closed boundary of the domain. You can see in the first diagram, elliptic problem. Then last one is our hyperbolic. So the solution domain of hyperbolic partial differential equation has the same open-ended nature as in parabolic PDE. However, two initial conditions are required to start the solution of hyperbolic equation, in contrast with parabolic equation, where only one initial condition is required. So the difference between this, there are two initial conditions are required to start the solution of hyperbolic equation, in contrast with the parabolic equation, where only one condition is required. This we have already discussed. Numerical errors we can discuss more. Relatively low cost, then speed, ability to simulate real condition, ideal condition, comprehensive information. The limitation is physical models. Numerical errors we can discuss more, and then boundary conditions. So there are mainly when we are doing the CFD problems, so there are three basic or three major, we can say, numerical errors. The first one is round off error, the second one is truncation error, and the last one is our discretization error. So in the round off error, it is, we can say, introduced because of computer inability to handle large number of significant digits. Typically in single precision, the number of significant figure ranges from 7 to 16. It may vary from one computer system to another also. So this round-off error arises due to the fact that a finite number of significant digits or decimal places are retained and all real number are rounded off by the computer. So the last retained digit is rounded off if the first discarded digit is equal to, or we can say, greater than 5. Otherwise, it is unchanged. Then there is a second one is our truncation error. So the truncation error is due to the replacement of an exact mathematical expression by a numerical approximation. So this error has basically, it is the, we can say, difference between an exact expression and the corresponding truncated form, like we can say in truncated Taylor series, or we can use in this numerical solution. Then last is our discretization error. So the discretization error is the error in the overall solution that results from the truncation error, assuming the round off error to be negligible. In mathematical terms, we can say discretization error is equal to exact solution minus numerical solution with no round off error. So there are basically, when we are doing this any numerical analysis, or we can say CFD problem, so there are three boundary conditions, initial and boundary condition. We can see in this, the first one is our Dirichlet condition, first kind. You can see in the diagram also. The second one is Newman conditions, and the last one is our Robinson condition, third kind. So these are the basic steps which we are using in the CFD. The first one is our problem identification and pre-processing, which we have already discussed. Define your modeling goals, identifying the domain with what we need, and design and create the grid also. Then after that, solver execution, set up the numerical model, where we have to choose according to our problem what are the different equations, partial differential equations, or conservation of mass, momentum, energy, that we have to choose in the solver execution. And the last one is our post-processing, where we have just examined the result and how we can plot or how we can present the results in the different forms. How we can use this CFD packages. The first one is, before starting any problem in the CFD, there are two main things we have to use, or we should do. The first one is our grid independent test, GIT in the short form, and the second one is validation is very important. Without validation, we cannot start our problem. So there is some important issue involved in the using CFD, like mesh independence check, selection of an appropriate turbulence model, validation of the solution based on a simplified problem which contains the important features similar to our problem, and careful interpretation of our results. So these are the main things which we have to care about that. As I told, validation is very important before starting the any CFD problem. The validation is, we can take any, for suppose we are talking about room airflow. So 20 years back or 10 years back, any researcher have done the experimenter for room airflow or empty room. So we can take the data for this experimented, and the same boundary conditions or same geometry we have to make in our numerical, and whatever results he was obtained at that time, we can just obtain that close to that results, like your velocity contour, temperature contour, particle tracking, anything which we have to first validate. After that, in that room, we can change the geometry also. We can change the inside the room. We can put some heat sources also, compared with analytical solutions, checked by intuition's common sense, and compared with other codes also. So coding validation is also there. So in this, just I have shown the geometry and mesh building intelligent toolkit. So there is a nowadays Gamebit is now not using. Everyone is using, I think, this. You can use the ProE, AutoCAD, CATIA also, but there are, when we are import, so there are some errors will come. So better we can create a geometry in a design modeler or whatever in the already exist in the ANSYS. So the first geometry creation, important import from CAD, CAE or previously generated mesh file, clean up and decompose into meshable section, then meshing, local meshing edge boundary, then layers and size functions, global meshing, phase and volume. First, we have to examine mesh quality, boundary conditions and continuum zones assignment, and then export to the mesh to the fluent. So this discretization, this finite volume method, we know that we need to divide the whole problem domain into many small domains, then integrated at these small domains. This is grid generation. We have 3 methods to generate the grid. The simplest one is structure grid. This type of grid, all nodes have the same number of elements around it. We can describe and store them easily. But this type of grid is only for the simple domain, or we can say simple geometry. Then we have a complex domain. We can use unstructured grid. For example, this is a complex object. The flow near the object is very important and complex. We need very fine grid at this region. Then when we moving far away from the airfoil, for example, the flow is comparatively simple, so we can use coarse grid. So generally, unstructured grid is suitable for all geometry. It is very popular in CFD. The disadvantage is that because of the data structure is irregular, it is more difficult to describe and store them. So block structure grid is a compromising of structured and unstructured grid. The idea is firstly divide the domain into several blocks, then use different structure grid in different blocks. There is a one value which is very important, where we can say y plus value. Y plus, what is y plus value in the CFD? So this y plus is a non-dimensional distance from the wall to the first mesh node. We can see in the different problems, which is very important for this y plus value, to use a wall function approach for a particular turbulence model with confidence. We need to ensure that our y plus values are within a certain range. So this is the diagram of structure grid. All nodes have the same number of elements around it, only for the simple domain, or we can say simple geometry or simple problem also. Then for unstructured grid, in that for all geometries or irregular data structure. And then last one is our block structure grid. Then discretization, there are three basic methods. The first one is a finite difference, straightforward to apply, simple structured grid. Then finite element for any geometry. And then last is our finite volume, conservation, and we can apply in any geometry. So what is the meaning of this discretization? So the act, or we can say process of making mathematically discrete, the process of dividing a geometry into a finite element to prepare for analysis, that we can say discretization. So this finite volume method is a method for representing or and we can say evaluating partial differential equation in the form of algebraic equations. Another advantage of the finite volume method is that it is easily formulated to allow for unstructured meshes. The method is used in many computational fluid dynamic packages. So what will be the difference between this FEM and FDM, means finite element and finite difference method? So in the finite difference method, the discretization of the domain is done as a set of nodes at which the results are determined. While in the FEM method, the results are known in every point of the computational domain, or we can say problem domain, as the approximation is done with functions defined on small triangular areas in the 2D. Then what is the difference between this FEM and FEA? So finite element method refers mostly to complex mathematical procedures used in mathematics. So FEA is usually used in the context of applying FEM to solve a real engineering problem. So the main advantage as well as main disadvantage of finite element is that it is a mathematical approach that is difficult to put any physical significance on the terms in the algebraic equations. So in FEM, we are always dealing with fluxes, not so with finite elements. So the FEM is a method for representing and evaluating PDEs, that is partial differential equations, in the form of algebraic equations. And another advantage of the finite volume method is that it is easily formulated to allow this unstructured meshes. So these are the basic governing equation. As I start of this talk, as I discussed, there are three basic governing equation which we are using in the CFD. That is our conservation of mass, that is related to continuity equation. The second one is our conservation of momentum, or we can say Newton's second law of motion, which is related to Newton's second law of motion. And then conservation of energy, which is related to first law of thermodynamics. So the rate of change of energy equals the sum of rate of heat addition to and work done on fluid particle. So these are the equations which we have to use in the continuity, momentum, and energy equations. In the combined, if we talk about this, so there is a one differential equation and integral form of the general transport equation which we are using in our CFD problems. In that, the rate of change of energy for the energy equation, we can say the rate of change of energy is equal to the sum of the rate of heat addition and the rate of work done on a fluid particle. Then if we talk about this equation, this differential and integral form of the general transport equation, so it clearly highlights the various transport processes. The first one is our convective term, left-hand side, or we can say rate of change term. Then the second term is our diffusive term. Then last is our source term on the right-hand side. So in order to bring out the common features, we have had to hide the terms that are not shared between the equation and the source term. So in this equation, it can be made to work for the internal energy equation by changing I into T, or vice versa by means of equation of state. So these are the two researchers, the Navier-Stokes equation, which are well known in the fluid mechanics. In this slides also again, the differential form I have shown, the continuity equation, momentum equation, and internal energy equation. Then what cannot CFD do? So CFD is still struggling to predict even the simplest flow reliably. For example, a jet impinging on a wall, we can say heat transfer in a vertical pipe, then flow over a pipe and combustion in an engine. Nowadays we can do, but still there are some drawbacks or not up to the mark results we can achieve. So important conclusions is validation is of vital importance to CFD. As I discussed, the validation is very important before going to our problem domain, or the second one is our grid independent test, that is GIT. Uses of CFD requires more expertise than many other areas. CFD solutions beyond validations are often sought, and expertise plays an important role. So these are the some important definition which we are using in the CFD, like turbulence intensity ratio, viscosity ratio, length scale, dissipation rate. And the dissipation rate is the kinetic energy of turbulence, is the rate at which the turbulence energy is observed by breaking the eddies down into smaller and smaller eddies until it is ultimately converted into heat by viscous force. Then there is a energy cascade process in turbulence, dissipation rate, consistency. Consistency is like a numerical scheme is consistent if its discrete operator with finite difference converges towards the continuous operator of the partial differential equation. Then stability is there. So mathematical field of numerical analysis, numerical stability is a generally desirable property of numerical algorithms. Calculation that can be proven not to magnify approximation errors are generally called stable. Then there is a convergence also. So in that, generally this numerical model is converged if and only if a sequence of model solutions with increasingly refined solution domain approaches a fixed value. Furthermore, we can say a numerical model is consistent only if the if this sequences converges to the solution of the continuous equations which govern the physical phenomena being modeled. Then there is a case study which I have to discuss with. There is a first, I have done this experimental work. So this, I have taken a plexiglass. The results obtained for this indoor temperature conditions in an occupied chamber have been compared and well validated with the similar model used for indoor quality analysis by experimental method and numerical method. After comparing this results trends in an unoccupied chamber with existing experimental and numerical, a similar profile, variation, and pattern can be plotted. And after comparing the numerical results of thermal comfort with numerical and experimental studies, the maximum deviation of 2% or plus minus 5% can be observed in the indoor air temperature. For further validation of the flow field, the experimental analysis has been carried out on the model. We can see in this diagram. So before starting this results parts for this, how this or how much important this room air flow problem or indoor thermal comfort. So in solving fluid flow problems, we need to aware that the underlying physics is complex and the results generated by a CFD code are at best as good as the physics, and at worst as good as its operator. So elaborating on the later issue first, the user of a code must have skills in a number of areas. Prior to setting up and running a CFD simulation, there is a stage of identification and formulation of the flow problem. in terms of the physical and chemical phenomena that need to be considered. So typical decisions that might be needed, or we can say the model of a problem in 2 or 3 dimensions to exclude the effects of ambient temperature or pressure variation on the density of an airflow, to choose the solve the turbulent flow equations, or to neglect the effect of small air bubbles dissolved in tap water. So to make the right choices requires good modeling skills, because in all but the simple problems, we need to make assumptions to reduce the complexity to a manageable level, preserving the salient features of the problem at hand. It is the appropriateness of the simplification introduced at this stage. So the user must continually be aware of all the assumptions, clear cut and that have been made. Performing the computational itself require operator skills of a different kind. Specification of the domain geometry and grid designs are the main task at the input stage, and subsequently the user needs to obtain successful simulation results. So the 2 aspects that characterize such a results are converge and grid independence. So the solution algorithm is iterative in nature, and in a converged solution, the so-called residual measure of all overall conservation of the flow properties. Then progress towards a converged solution can be greatly assisted by careful selection of the setting of variation, relaxation factor and acceleration devices. There are no straightforward guidelines for making these choices, since they are problem dependent. So optimization of the solution speed requires considerable experience with the code itself, which can only be acquired by extensive use. So there is no formal way of estimating the errors introduced by inadequate grid design for a general flow. So good initial grid design relies largely on an insight into the expected properties of the flow. So backward in the fluid dynamics of the particular problem certainly helps, and experience with gridding of similar problems in also invaluable. So the only way to eliminate the errors due to coarseness of a grid is to perform a grid independence study, which is a procedure of successive refinement of an initially coarse grid until certain key results do not change. So then the simulation is grid independent. A systematic search for grid independent results from an essential part of all high quality CFD studies. So every numerical algorithm has its own characteristic error patterns. Well known this CFD, the term error are terms such as numerical diffusion, or we can say false diffusion, or we can say even numerical flow also. So the likely error pattern can only be guessed on the basis of a thorough knowledge of the algorithm. At the end of the simulation, the user must make a judgment whether the results are good enough. It is impossible to access the validity of the model of physics and chemistry embedded in a problem as complex as a CFD code, or the accuracy of its final results by any means other than comparison with experimental test work. So anyone wishing to use CFD in a serious way must realize that it is not substitute for experimentation, but a very powerful additional problem solving tool. So validation of a CFD code requires highly detailed information concerning the boundary conditions of a problem, and generates a large volume of results. To validate this in a meaningful way, it is necessary to produce experimental data of similar scope. This may involve a program of flow velocity measurement with hot wire anemometer, laser droplet anemometer, or particle image velocity meter, PIV. So however, if the environment is too hostile for such delicate laboratory equipment, or if it is simply not available. Static pressure, temperature measurement complemented by pitot static tube transfer can also be useful to validate some aspect of a flow field. So in this, I have taken the airflow pattern by visualization. So there are two types of validation I have taken. The first is experimental versus numerical, and the second one is our this visualization versus numerical one. So the experimental analysis has been carried out on the model we can see in this diagram for verifying existing physical principle and discovering flow phenomena. Flow visualization is the leading tool in this experiment. The fluid flow pattern can be visualized by sending visible particles through the practice of an illumination sheet. And this many researchers uses this technique in the studies of indoor air quality, or we can say thermal comfort, as it provides useful information about the flow field, but only qualitative flow field facts can be expected. So the subsequent experiments arrangement has been used for the validation of numerically modeled occupied rooms. The geometry model of a 4-bed, you can see, I've taken the first one left hand side. There are 4 beds, and in the second setup, there are 2 beds, ICU room with a partition. I have create one partition also between the two patient, we can say. So the size of this validation of the study has measurement of 1835 cross 1225 and same geometry 1225 millimeter cube. So it consists of 4 occupants and beds of 40, 140, 455 millimeter cube and 250 cross 350 and cross 500 millimeter cube correspondingly. So to ensure the essential uniform and steady airflow at the entrance to the model room, we can use 1500 millimeter long duct is intended. So fresh air enters through the inlet vent using a duct and leaving the outlet vent located on the opposite wall. So the flow visualization is achieved by smoke injection in the room and then capturing the indoor airflow pattern. The smoke particles stream the indoor airflow pathway for the airflow setting. The airflow is produced by a fan. The indoor airflow pattern can be observed due to the visible smoke and can be captured using a fixed camera. And experimental measurement of recording air velocity, air temperature, and visualization smoke concentration have been taken after more than 3 hours complete attainment of thermal and fluid steady state. So for temperature measurement, a thermal anemometer was used to keep a count of the indoor air velocity throughout the experimentation. To measure the experimental velocity of the thermal anemometer, a 1000 cross 30 millimeter square identical slot is generated in a room with 6 millimeter holes every 100 millimeter. So the simulated and experimental outcome of the velocity vector for the 4-bed model room, while the inlet velocity was kept constant at 0.2 meters per second. Similar and acceptable flow patterns were observed in the comparison of numerical and experimental results. Then the second one is experimentally model arrangement for the 2-bedroom considered for validation. The similar measurements of the room are considered as a 4-bed room model. The room arrangement of the 2-bed room consists of the 2 occupants and bed. The dimension of both are considered similar for the just previous model, and each occupant is placed at the center of the room, and the difference between the 2 patients, it's 330 millimeter away. The mainstream from the entrance hits the ceiling, hits the opposed wall and travels towards the flow. At a steady state, the stagnant zone is observed below the inlet vent. An easily visible recirculating zone has formed among the north wall and the occupants. The indoor smoke gradually escapes from the exit vent and we can see easily in the right side of this diagram. So there is a stagnant zone in the lower left corner that can be seen both the simulated and experimental results. The numerical simulated and experimental visualization results match and the airflow pattern seen comparable, and it shows the outcome of the numerically simulated velocity vector and the experimental visualization. So for the second case, two-bed model, while the inlet velocity is kept constant at a velocity of 0.2 meters per second. So the stagnant zone can be observed in the left bottom corner in the both numerical and experimental. From this, we can conclude, or we can see that the results for this numerical and experimental, similar visual results we can achieve. So therefore, it's set up to avoid cost of experimental errors. Acceptable results can be obtained from numerical simulation using CFD software package or techniques, and can be considered as precise as the experimental results. So the indoor arrangement for the of the furniture in the present study has been altered and on compare with experimental investigation, and under identical boundary conditions shows the acceptable outcomes. Then this one is our base geometric model. As I told, after validation, we can change the geometry also, or we can put inside, like in this diagram also, we can see the small components like office room. I have taken this double panel radiator, then human occupants, then CPU, monitor, chair, table, inlet and exhaust vents and walls, floor, ceiling. So the thermal, we are talking about thermal comfort in this. So in the thermal comfort is the mental state that articulates satisfaction with the IEQ, and it is estimated by subjective assessment. So indoor thermal comfort and indoor air quality are the main components of indoor this problem. Although the flexibility provides on the factor that affects the indoor temperature, thermal comfort is always more than the indoor air quality, since it affects more indoor occupants' thermal comfort and has the energy consumptions of the building. So it is important to analyze and optimize the factor that affects indoor thermal comfort. So external factors such as the ambient environment, and indoor factors such as internal heat generation due to the basal metabolic rate of an individuals that controls the temperature of the human body. Even under the effect of these factors, the human body continuously maintains the body surface temperature in the range of 28 degree to 32 degrees Celsius with the help of unremitting heat exchanges with the surrounding. For a high activity level, the skin temperature rises about 34 degrees Celsius. The human body continuously exchanges energy with the surrounding by convection, radiation, and evaporation as per the requirement to maintain the body temperature. So overall, there are two main factors that affects the occupants' indoor thermal comfort are psychological and psychological aspects. Most studies focus on psychological parameters rather than analysis of a psychological parameter, as there are some limitations and there is no specific investigating method. So the previous researcher developed the standard set of questionnaires to take comments for render occupants to analyze the indoor thermal comfort and the psychological parameter. So in this method, the collection of authenticated data is very difficult and outcomes can be misleading. So these psychological factors mainly consist of environmental and personal factors. So environmental factor focuses on air temperature, relative humidity, comfort temperature, operative temperature, then we can say radiation temperature, ambient climate conditions, and we can say air speed also. So among all these factors, the air temperature and the speed in the occupied zone, we are more focused on the occupied zone, not above the occupied zone of the building, influences the indoor thermal comfort, since the human body dissipates 75% of the body heat by convection and radiation to the surrounding air. So the main components that influence radiation and convection air, temperature, or we can say skin temperature, and air velocity adjacent to the occupants, acknowledged as in the occupied zone only. So in this model, the description is like this numerically, naturally, we can say ventilated room with a cross ventilation system with a measurement of 4.8 meter cross in the length, and in the height is 2.7 meter, and the width it's 2.4 meter. We have generated this in the ICM CFD software. And a small office was built with isolated wall comprising floor and ceiling. Then there is a glazed glass window, double panel radiator, occupants, furniture, internal heat generation source like we can see here CPU, then inlet and outlet ventilation on an opposite wall as shown in the diagram. So the furniture installed in the room consists of a couple of tables and a sitting chair, while the internal heat generation source are the block-shaped occupants, then CPU and this monitor. So the occupant sitting on the chair is thought to be working on the computer, and therefore the computer is generating internal heat flux. So the occupant sitting on the chair and the working at the computer is taken as 1.3 meter above ground. The table design is kept 0.05 meter from the walls to create a fluid domain around the internal heat generation surfaces. So for detailed geometric this specification, we can just check this furniture, occupants, the size and place in the room. So this 3D model geometry has been meshed using the ICM CFD package software, we can say, using unstructured hexamesh, and for more accurate and real-time simulating outcomes. The regions near the radiator, human occupants, and all the internal heat generating source have finely meshed for more accuracy, and the mesh is in the fluid domain. Other than internal heat generating sources kept coarser than the region with higher flow and heat interaction. So the unstructured mesh, as I told, we have used for surface hexamesh, and we are using this package 18.2 CFD NSYS to main simulation tool for this present work, which is accurate and simplifies the application of airflow modeling tools in the design and analysis of ventilation system essential for our this internal thermal comfort and energy efficient building. So the complex indoor fluid flow, this CFD tool is very effectively and widely used to study the indoor quality and air quality to simulate the real indoor environment. For the discretization, the finite volume method is adopted, and the resolution techniques for this simple algorithm, this is semi-implicit method pressure linked equation for the pressure and velocity coupling is adopted. And for post-processing, different software is used as required, such as CFD Post Analyzer, TechPlot, Origin, ParaView, and others also. So the boundary condition for this geometry, the indoor air temperature, the setup is 16 degrees Celsius as an initial patch condition. The building envelope comprises 6 walls, counting a roof, floor, and a glazed glass window to allow adequate natural light to enter the room. All the bounding surfaces of an envelope are considered isolated, and the temperature of the glass window is kept constant at around 14 degrees Celsius. So the window is located exactly above the double panel radiator. So it is assumed that the window can maintain its constant surface temperature of 14 degrees Celsius. Since the heat transfer occurs due to natural convection, so the factor influencing natural convection are taken into account for boundary conditions such as thermal conductivity, then density, then coefficient of thermal expansion, specific heat. Then these occupants are expected to be comfortably seated on the chair and perform some low activity work such as reading or writing on the monitor. As occupants have low activity, the metabolic rates are also low, but can significantly affect indoor thermal comfort. As the objective of this present study is to analyze the ITC, the occupant's metabolic rate was kept constant throughout the study, like is constant, we can say 1.1 for the low activity level to maintain constant skin temperature. So the total surface volume of the occupants is measured as 0.18 to 0.2 meter cube. The indoor furniture such as chair, table is considered non-heat generating surfaces made of wood. The monitor, CPU, and occupants are the continuous source of internal heat generation. When the monitor and the CPU are turned on continuously for a long time due to energy conversion, and they act as an internal heat source and can alter the internal thermal comfort also. So as with winter heating, the clothing insulation of the occupants is adjusted according to the cold climate conditions. Then we can take this ambient cold air at 5 degrees centigrade, enters the room and at the velocity of 0.7 meters per second, and therefore due to the low velocity inlet, the flow is considered incompressible at the inlet. The double panel radiator is installed on the inlet wall just below the glass window and maintained at a constant heat flux to retain the surface temperature at 30 degrees Celsius to maintain an acceptable internal thermal comfort. So the equation of energy and moment of continuity were evaluated for the modeled 3D occupied indoor environment by the CFD program. The K epsilon turbulent model of the two standard equations and the Reynolds average Navier-Stokes RANS equations are employed together to solve the computational problem. As the geometry consists of several wall surfaces, the flow pattern and near the wall also affect the thermal comfort. Therefore, the improved wall treatment scheme is employed with the turbulent model for high computational precision. The standard K epsilon method, we can say turbulence model, we are using to predict airflow and turbulence in a bounded environment in very efficiently with a high computational economy. Then in this natural convection heat transfer problem, the Boyznik approximation has been used to capture the effect of change in density of indoor air due to temperature difference. In highly buoyant flow, body weightage schemes effectively interpolate the pressure and the other properties. A discrete radiation model captures the effect of radiation emitted by the various internal heat generating sources effectively and hence employed for the present work. And the model can be well pragmatic to study the effect of radiation from closed indoor radiating surfaces. The geometry has finally meshed with the unstructured hexagonal mesh. The mesh was kept very fine close to the occupants and all heat sources to accurate capture heat flow and transfer. As I told, the semi-implicit method pressure link equation algorithm has been used for this second order discretization techniques to resolve the non-linearity of the velocity pressure coupling, momentum equation, and interpolation of scalar and cell faces respectively. So the numerical simulation of the deliberate problems was carried out by resolving the mass, conservation of mass, momentum, and energy equations. The equation of the turbulent model and the discrete ordinate radiation model have been solved to calculate the effect of turbulence and radiation. So in this computational fluid dynamics, the transport equations are solved for turbulent flows and the energy equation in the form of radiation models is solved for the heat transfer problem. So as I told, there is first we have to do this grid independent test and specification of model before going to our problem. So ICM CFD software has been used to generate the geometric model and unstructured hexagonal mesh to create the nodes and elements. The complexity of the geometric model requires the mesh independence test to study the effect of the mesh on the simulation results. The mesh independent tests play a very important role in the accuracy and cost related to CFD simulation. We can check if the model is independent of the mesh size used. There are 3 geometric model with a mesh resolution of 1,79,000. Then the second one is our 2,89,000, and the last one is our 3,86,000 nodes have been generated and compared with the indoor thermal comfort temperature. And it is verified that the comfort temperature for the 3 grid sizes found is similar, with the variation is less than plus minus 0.07 degrees Celsius. So while the mesh with 1,79,000 and 2,89,000 nodes shows the same results for the thermal comfort temperature, so we are choosing any of the meshes can be used for further analysis, and we can conclude that the model has meshed independently. For lower cost and computational power requirement, a mesh with a lesser number of nodes can be selected. For a higher factor of safety in the study of cold climate condition, the unstructured hexagonal mesh with 3,86,000 nodes was chosen, and it provides a relatively lower temperature compared to other mesh size. Then in this, the forecast of this indoor thermal comfort can be evaluated using the Fenger equation of the PMV and PPD index. The effect of physical parameters like air temperature, air velocity, mean radiation temperature, humidity, clothing insulation, and metabolic rates of an occupant has been combined by Fenger's model. As per the ISO 7730 guideline, the acceptable index is between plus minus 0.5 for a critical analysis of comfort in the occupant range. The occupant body is segmented into 4 main parts. So independent of this PMV, indices were plotted for the 4 parts of the body to analyze the overall comfort of an occupant. So for calculation simplicity, the average PPD and PMV values along the length of each segmented body parts has been taken. So for this present study, we are choosing this 0 degree in the index for the thigh, head, and body shows almost the same values, but the PMV index for the leg varies considerably from the other parts of the body. So the same observation can be made in all other cases for different angles. I have not shown all the results in this slide. So we can say that the leg is of the seated occupant is the most affected part of the body. This concludes that the occupant's legs are more sensitive to indoor thermal comfort. Therefore, while calculating the thermal comfort in the indoor environment, special attention should be given to the indoor thermal comfort in the occupied zone near the occupant's legs. The occupant's legs are adjacent to the floor, and from all the sections discussed above, we find that the air temperature, radiation temperature, and airspeed fluctuations are highest in the floor region, and this variation may alter the occupant's perception predicted for the indoor thermal comfort. So from this diagram, it is observed that the occupants are more comfortable within 30 degree and experience discomfort with around in 75 degree. For a better, we can say, understanding of this rating, the polar graph is plotted for different parts of the body and at different polar angles also. And this figure shows this PMB index for the different parts of the body and represents the mean PMB index for the occupant's body. Since this is a cold climate study, efforts have been made to keep the indoor climates slightly warmer than required, and care has been taken not to lower the PMB index in cold climate conditions. So this condition is followed by 15 degree to 30 degree, while 30 degree shows the values closest to the neutral value on the PMB scale. So the index follow the same pattern for all parts of the body and means that the ITC in the occupied zone is adequate, while the legs are more sensitive to ITC, indoor thermal comfort, and this can lead to occupant dissatisfaction. So to deepen the analysis of the ITC, the percentage of people dissatisfied with the ITC must be determined. These are some results which I have shown. Not all the results I have not taken in these slides. These are some resources. CFD software was built upon physics, modeling, numerics, two types of level software like our commercial and research. Then we can take some information from these links also. COMSOL, then GridGen, GridPro for the grid generation software. Then the last one is our visualization software, that is TechPlot and FieldView. And well known is our CFD software Fluent, in which we are working. It comes under the ANSYS. Then the conclusion, as I told, there is no specific, it is a general conclusion, which I have already discussed. This is beneficial because it is very user-friendly way to quickly solve many different types of flow problems. Then it provides user with a general understanding of fluid mechanics, a tool to solve otherwise very complex fluid flow problems, ability to simulate realistic and ideal, as I already discussed. And the last one is it provides comprehensive information, like if in room airflow problem, each and every point we can achieve, we can determine, and we can find the values of your density, temperature, pressure, viscosity. Each and every point we can find the values of different thermodynamic properties also, we can say. So it provides a comprehensive information. So thank you for the patience. Any queries from the participant side, then please, or you can drop a message also.
Thank you, Dr. Verma, for delivering a talk in a very interesting topic. And you told you start from basics, and you have explained about the practical and experimental applications of computational fluid dynamics. Now I request the participants, if they want to ask any questions, please ask one by one. Raise your hand. I will call the name. Am I audible?
Yes, sir, you are audible, sir.
Yes. So, participants, is there any question?
Jyotindra Kumar Pathak has raised hand.
Amit Kachwaha. Mr. Amit? Dr. Jyotindra? Dr. Jyotindra Kumar Pathak?
Okay, anyone have any doubt regarding my area? Because in the CFD, there is a lot of areas to work in the fluid flow and heat transfer. So if anyone wants to know how to use the CFD package in the room airflow problem, then they can drop a mail also, and they can contact me in phone also. There is no problem. Other than this, I can work in the heat exchanger problem also. As I told, this CFD package or CFD software are using in different ways in the different engineering problems. So I am not expert in each and every problem. but we can say कि room airflow and heat exchanger problem I can help if anyone have any doubt related to that problems.
Yes.
Tirath Malay has raised hand.
Yes. One participant is asking,
Hussein
can we use CFD in microprocessor?
Yes, definitely we can use this CFD package in microprocessor. One of my friend is working in this in IIT Guwahati also. Now, exactly what he's doing, I don't know, but definitely this CFD package we can use in the microprocessor also. Confirm.
So I am concluding the meeting here. I request all the participant, can you switch on your camera for 1 minute? We want to take a group photograph. Dr. Tikendra Nath Verma, I request to all of you. I request the participants, please switch on their camera. So, Mr. Rathore. Okay. So, thank you. Thank you, Verma sir, for giving very informative talk. And we'll see you in the next session, in the 13th session, where you are going to discuss about the biofuels. Our next speaker is also here, Sanjay sir.
Yes, sir.
If you permit, can we give a break for 10 minutes, because participants are here from past 1 hour 30 minutes. So
Yeah, sure,
they will
please.
also.
Sure.
Yes, sir. So I request all the participants that we are closing this session here, and we will again join at 7:45 after 15 minutes of break. Our next speaker is Mr. Sanjay Namdev sir. So we will start the session exactly at 7:45. And I am again thankful to Dr. Verma for accepting our invitation to deliver talk in this faculty development program. Thank you, sir.
Okay, thank you, sir.
Okay. Dr. Murli, kindly
Yes,
stop
sir.
the recordings and close the session. Then
Yes,
we'll start at 7:45. I request